Okay.
If your resume isn't getting traction, might be time to change up your strategy, see what the data actually says about successful job applications.
Okay. Um, for some reason my camera is not appearing. Just a minute. Okay. So good morning, everyone. All right. So good morning once again. Um, so today we are going to um, go over the things that we talked about last time. Um, I know it was kind of a handful for a lot of people, some of you. So I thought I should go over the lecture so as to better address some of the problems that you might have. Okay. All right. So once again, welcome. If you have any questions, I'm looking at your live comments. You can always post it, and I'll try my best to answer your questions. So we'll start. Today we go over what we did last time, and specifically we are talking about computer vision. Okay. So let me also say this. The data set or the example that we have in this notebook is kind of generic. Okay. But you can actually reposition it or repurpose it for your own personal project. So you can think of any personal project that you might want to do. Okay. Collect the data and fill you the code that you have in this notebook to um, to hey, the sound is not clear. Just a moment. All right, so I don't know if it's a lot clearer now. Um, okay. The person that said the sound is not clear, I don't know if it's better now. Is it better now? The audio. Okay. All right, so I'll try to see if I can speak a little bit louder. Okay. Working on my audio. Yep. So my microphone is almost on full throttle right now. All right, so let me quickly disconnect and connect again. All right. I don't know if you can see, you can hear me clearly. Then I think the audio is much better. Okay. So please let me know if the audio is a lot better now. Yeah, I know you can see anything for now, but I'm working on the audio. If you can see me, just let me know. If you can hear me, actually, is the audio better now? Okay. All right. Fine. Okay. How good is the audio now? All right. Fine. Good. So once again, good morning. If you can hear me, if you can't hear me, then I think that will be a network. Other people are saying it's like that. Okay, so good morning. Today, our focus is still on the last lecture. So we're looking at computer vision. So like I said a while ago, if you have a personal project, if you aside the one that we are discussing here, you can still use this code for that personal project. Okay. So in fact, I actually encourage you to do that. But the data set that you're using here, it's synthetic. So it's right. It's just a demonstration for here. You can think of project, collect the data, and you use this to okay. If you have any questions, you can always contact us. We'll guide you for it. All right. So what is computer vision? It's just the act of teaching the computer to see. Okay. That's basically it. So we want to um, make the computer to be able to identify or recognize things, visual things, hence the word vision. Okay. So specific tasks could be classification. Okay. It could be segmentation. Okay. So it will also be object detection. So this is what we are talking about here. So it could be that we want to, take a picture and show it to the computer and ask the computer to identify whether a specific object is present in that picture, in that image, or in that video. In which case, that is called an object detection task. Okay. It could also be that we want the computer to be able to classify, or you can put it in a different way, categorize certain images. Okay. For example, you want the computer to be able to identify the different type of food present in the image. In this case, there's a pizza here, and this is some omelette. Okay. So if there are just two categories, we call it binary classification because it's just two. Okay. If there's more than that, we call it multi-classification. Okay. It could also be a segmentation problem where we give the computer an image and we want the computer to be able to, sieve off the background, okay, and only focus on some foreground that we care about. And this is what is the preferred here. Okay. And a lot of people do this. People do this a lot for images. If you go over Snapchat, there are some filters that are able to extract or segment the image based on certain features or certain object of interest. Okay. So what we are about to cover is the entire training pipeline. Okay. Somebody says like tractors using in modern agriculture. I don't know how that fits. Well, you can think of a typical use case to be, let's say, for example, you want a robotic arm to maybe look at a train of fresh, maybe vegetables or maybe fresh apples, and then you can build a computer vision system that recognizes whether the apples are fresh or bad. Okay, so if you put that in a robotic arm, then of course, as the conveyor belt is moving the apples or moving the fruit, whatever fruits it is, you can now, and if it detects that the particular fruit is faulty or bad, you can put it in a different tray, okay? And if the fruit is not faulty, you can put it in a different tray. That's the particular use case, okay, that I can think of for agriculture. But in general, this is typically what you do in for self-driving cars. If you have let's say you want the car to be able to detect whether a pedestrian is crossing or not crossing. Okay, so as the car is driving, there's a camera view, traces the camera view of its environment, and you want the model to be able to detect whether there is the presence of the pedestrian or not, so that the brakes can be applied. So yes, it can be also, in fact, used heavily in self-driving cars. Okay, so like I said, the general pipeline remains the same. Okay, you get the data, okay, and you can pick a model. Okay, by this I mean, well, there are some models that have been trained for a particular task. Okay, you can pick that model and fine tune it for the task that you want to do. Okay, and so this is the teaching parts, and then you evaluate the model. Okay, you can improve it through various experiments. You can save the model and reload it, you know, and reload the model maybe for other use. And if you look at this picture, it shows the various libraries that you need to do all this. For example, um, to build and fit a pre-trained model, can use um, touch.nm or touch.nm.modules or touch.nm.models. Okay. For optimization, we use touch.team. Okay. This is very, very important, getting the data ready for your model. Okay. The libraries that we are going to be using the touch transform to transform the inputs to different um, from one input to another inputs. Okay. For people who are mathematically inclined, you can think of it as a map from one space to another. Um, so that's what these transforms do. And then the data sets gives available. There are some data sets that have been curated. Okay, so we can download them in this library. But very, very important, you will need the data loader. Okay, this is able to manage how you pull the data from wherever you to save the data. So these are all the things we're going to get into. Okay. All right. So the topic is, well, we load the data, we'll prepare the data, we'll build a baseline model, like a simple model. Okay. We make predictions. We set up a new device agnostic code for future model. What does this mean? We see it in moments. We are going to add non-linearity to see if it improves the network. And then we are also going to look at convolutional neural network. Okay, we compare the models, and we're going to look at something called confusion matrix, since we're doing classification problem. Okay. All right, so you can get more materials from this link. Okay, for other topics or something that you can just go around with. Okay, so the first thing we're going to do is the libraries. Okay, the top vision contains data sets, already curated data sets, models that have already been built, image transforms and stuff like that. So under top vision, you have data sets, you have the models, you have the transforms, you have the data data sets, data sets, which is the base class for data sets, and then we also have the data here. All right, so let's get to work. So the first thing we're going to do, obviously, we're going to import all the things that we just calculated. Okay, so we import the neural network module. We import touch vision. Remember, touch vision, this guy here, contains a lot more. Okay, so we import the entire thing, and we specifically import data sets, and we import a particular transform class, which is called V2 tensor. So the essence of this is to take the representation of the data and transform it to tensor. Okay. If everything goes well, to start it. So if everything goes well, if you have all the items imported, then you should this code should be fine. Okay. All right, so that's good. So currently, my computer, I have PyTorch 2.3, and I don't have a GPU. I only have CPU. Okay, but like I said, we can build this code to be GPU agnostic. What that means is we'll set up the code in such a way that if we have a GPU to work, we will also have a CPU to work. Okay, so this is the data set that we're going to be using. It's called the FashionMNIST. Okay, it's just a very low resolution image of clothing items. Okay, And it's a multi-classification problem. Okay. So if you look closely, you see that each class is arranged sort of in a row, in rows. So these probably the shirts, these are the trousers, and so on and so forth. Okay. I think specifically for this problem, there are 10 different classes. Okay. All right. And then each class is represented by a number, which you'll see in a moment. Okay. So for some people who still you cannot hear me clearly, I think that will be your network because others can. So maybe if you can switch to the data network provider, that would help. So to get these data sets, like I said, it is inside touch.dataset of FashionMNIST. Okay. So this will enable us to download it from its repository. Okay. The materials have been posted on the Telegram channel, so you can always access it from there. In fact, I also posted a link a while ago before I started this instance. So this is it. So we download, we pull the FashionMNIST data sets. Okay. All right. So what are we pulling? We are pulling the training data set. Okay. Do you want to download it? Yes. Okay. Now, once it is downloaded, we want to take it to Tensor. All right. Do we want to transform the target tensor? No. Okay. So this will give us the training data. We do the same thing again for it, the test data. In this case, training is going to be false. And then the data you get will be for test. Okay. All right. So it may take a while for those of you who haven't done it before, but I have. So this is why it's a little bit, it's a lot faster. Okay. So I have the reference to my train data. I also have the reference to my test data from this code. Okay. I can just take a look. Okay. All right. So from the train data, I can just get the first item, which is indexed at 0. Okay. Now, if you do that, this is going to yield 2 references, one for image and one for label. And this is why we reference like this. Okay. So I get the first item indexed at 0. Okay. And then I just print them out. All right. Okay. So you can see that, these are images, but what we get are actually numbers. I've said this several times. Images are numbers. Okay. Pixel values. All right. So there are lots of zeros here, and in some places there are 1. So these pixel values have been normalized. Okay. So the value is going from 0 to 1. That's what I mean. Okay. But 0 represents black. Okay. And 1 represents white. Okay. So this is actually an image, this tag here. Okay. Right. So this is actually an image followed by its label, because we're also printing out the label. Okay. So for this image, it is labeled as 9. What is 9? We will see, okay, in a moment. So for this image, it is labeled as 9. All right. So we can also look at the shape of this image. So if you can see, this is a 3D, 3-dimensional image. Okay. The first indicates the channel of the image. This is the height, and this is the width. Okay. There's one channel, height, and width. So it is a 28 by 28 pixel image. That's why I said it's a very low resolution. In real life, you're not going to have this kind of dimension. It's going to be much larger, which means you will be needing a lot more computing resource to be able to work with this kind of system. The channel indicates the color channel. So if the image is encoded as RGB, here will be 3, where R represents red, G represents green, and B represents blue. Okay, but because this is a black and white image, just one channel. Okay, so color channel, the height, and the width, and that is what's represented by these 3 numbers. There in case dimension. Okay. So once we get this data, we'll input it in a machine learning model. Okay, and we'll get a prediction. Okay, everything is in numbers. So we have the data, which is 28 by 28. They serve as inputs, okay, which will be transformed into tensors and we'll pass it to a machine learning model, okay, hoping that the output of that is going to give us some numbers as well, okay. So you can think of these numbers as probabilities, prediction probabilities, moving a particular weight, okay. All right. So the shape of this output is 10. And why is it so? This is because there are 10 categories of the FashionMNIST. Okay. So we want to look at the probability that an image belongs to a particular class. Okay. And that we can encode with the 10-dimensional graph. Okay. All right. So that's that. Now, usually, if you're not doing Python, maybe if you're doing TensorFlow, okay, images can be represented in different, shape order, okay. All right, so it could be that, so typically for the data you're going to get, okay, the data you're going to get, the shape is of the entire data set is going to be a 4D tensor, okay? Where the first dimension or the 0th dimension indicates the batch, okay? And then the rest will be about the image, okay? Now the image can be channel, like you see in this case, channel, height and width, okay? Or channel, or height and width and channel, okay? So this is what we're seeing here. So it can either be batch, height, width, and channel, or batch, channel, height, width, okay? And that is represented by this code here, okay? So here, there is no batch, okay? And you have the height and width in the channel. Here is no batch, it's with one channel, 28 by 28. So in real life, if you have a batch of 32, this is what you're going to get. 32 by height and width and one channel. Okay. In our case, we are going to get the batch by channel, by height, by width. So that's a 40 concept. Okay. So like I said, if the color index represented in RGB, the channel is going to be. So red stands for R stands for red, G stands for green, and B stands for blue. Okay. So this is our image that we downloaded. Let's take a look at the shape, okay? So we look at the length of the data, okay? And the length of the targets data. The target data is the label. We do the same thing for the text. So this tells us that there are 60,000 training images, okay? With their corresponding 60,000 labels, okay? And we're using 10,000 to test. 10,000 images and 10,000 labels for testing. Okay, so the next slide just visualizes these images. Okay, so to do that, we use the matplotlib. I'm sure some of you have seen this several times in previous lecture. We take the first image, okay, we print its shape, and then we do an InShape to just show it. Okay, but an InShow will take an image of 2 dimension, but we have 3 dimensions on this image, so we squeeze it. Okay, so squeezing it will get rid of this extra dimension. Then we can print the table. So if you run this, okay, the label is 9, all right, and this is the image. So this is probably some sandal. So, okay, so like I said, this is actually, so what you see is actually an array of numbers. These regions here, they're mostly zeros. Okay, these regions here, where the actual images are mostly ones. Okay, we can look at this whole thing in grayscale, okay, to get a clearer picture. So if I've not defined, I've not specified a particular code somewhere. Where is it? Okay. All right, so in the case of the image you just saw, it is actually labeled as attributes. And how do we do that? Remember, we get well, these are the classes. We have t-shirts, trousers, pullovers, and each of these are represented with a number. So obviously, t-shirts is going to be indexed 0, so which it means if you see a prediction of 0, it means that's a t-shirt. You see a prediction of 1, it means that's a trouser. You see a prediction of 9, it means that is an ankle boot. Okay, and since this is our data set, 9 indicates an ankle boot. Okay, and 4, this looks more like an ankle boot. Okay, you can see the actual label by doing the class name and you pass the label you get in the data set, which is really fun. Okay, in the same spirit, we can look at many of you can take a draw a sample from our training data set and just take a look at classes or the images that we're taking. So this is what this does. Okay, so we look at 16 images in total, so it's 4 by 4. Okay, so we do a 4 by 4 range, and then we take a sample. Okay, random integer from 0 to the length of the data, and then we use that to do a draw from the training data program as plots. So if you run that, this is the distribution of images that we are planning to train with. Okay, like I said, this is not restricted to. It's not restricted to. I think I've lost. Okay, all right. So this very code is not restricted to just this kind of data set. You can collect your own data set. Maybe for a fun project, you can use your mobile phone to take a few pictures and then see if you can train the model to maybe do classification for the image that you're taking. Okay. So for now, this is what we have. This is the training data set, and this some samples from the training. Okay. So now that we know the training data set that we're working with, we can just take a look. We can now prepare the data so that we can use it to train. And this is where the data loader comes in. Okay. All right. So the data loader does what you think it is. I mean, from the name, data loader, it loads the data. Okay. It helps you to load the data into the data. That's what it does. So if the data is very, very large, imagine if these images are maybe standard 200 by 200 pixels. Obviously, this will not fit into your memory, and this is where the data loader comes in. It will help you load them in batches, okay, manageable batches that your current computer can handle. Okay, so imagine if you have all these images, you don't expect me to load 60,000 images on this computer as it stands right now. It will crash, okay, because I don't have enough memory to load it. So in order to avoid these kind of problems, you need a data loader. Okay, so I can decide to now load maybe 16 at once, because I know my system can take 16. That's a batch. I can go 32 or 64, depending on the capacity of my computer. Okay, so this is what we're saying here. You can load them in batches or mini batches. Okay, so let's set up a data loader. First of all, to specify, we need to load 32 at a time. Okay, and then to set up a data loader is very simple. You just make an instance of data loader. You pass in the data you want to batch, and then the batch size. In this case, my batch size is 32, and I wanted to shuffle it each time it loads 32 batch. So I set this to true. We do this for the print, and we do this for the text. Okay, and just for sanity check, you can do some. You can print them out to see how they look. Okay, so if I print the data loader themselves, you can see that they are actually instances of the data loader object. So this is the memory. That's the memory reference. Okay, but then within the data loader, I can pick a length, which will give me the total batches. Okay, so if I have a batch of 32, all right, it means I'm going to have a total of 1,875. Each has 32 images. Okay, If you multiply these two together, you recover your 60,000. Okay. In the same way, I have 313 batches. If you multiply that by 62, you're going to get 10,000. Okay. Which tells you that it has been able to, divide up the data set in smaller chunks that you can now load in. Okay. You can, take a quick look at this data loader by iterating through it. Okay. So you can set up an iterator on the data loader that we just defined. If you call the next, it will retrieve batch of 32. So this is what this line does. Okay. And then the next line just prints the shape so that you see exactly what we're talking about. All right. So we run this, you see that we are now 32 bytes. That retrieved 32 bytes from our training data sets. Okay. Well, each byte is an image of one channel out of the representative. Okay. For the 32 bytes, of course, we expect to have 32 labels, which is exactly what you see here. Good. All right. So from that, I can. Well, this is simply just to do another sanity check to see that we are on track. Okay. All right. So that's our image. So let's now build a simple model to do this. So we're building a simple baseline model. Okay. It's a very simple model. It's just a linear model. Nothing so special. Okay. These are pixelated images. Okay. So we're building linear models. Remember, I told you these are neural network is just a bunch of notch multiplication. So we make a linear model, we flatten it at the ends, and then pass that, and that's an output. Okay, so see that how it works. Let's make a flattened instance. Okay, from this, then we can pick one image. All right. If you pass it, remember this image that we pick is going to be 1 by 28 by 28. If you flatten it up, it will be 1 times 28 times 28. That will give you, that's going to be the size of the word. Okay, so this is just to demonstrate that. Okay, so we print the shape of the image and we print the shape of this output, which flattens this image. So like I said, the shape of this image is 1 by 8 by 28. If you flatten this up, it means you're actually stretching it to a vector, which is 28 times 28 times 1. So that, or 28 times 28. So that gives you 1 by 784, which is 28 and 28. So this is the flattening. Okay. So follow it by, item. Okay. So that's that. So with that, we already know what we've already seen this in our previous session. Here we just build a simple model. Okay. All right. Because we are using our own custom data set, we obviously I think there are some tools that you can use to do this, but let's just focus on putting it. Okay. So it's very simple. Just make this is our model that extends the neural network model. We set up the constructors. Okay. So we expect that whenever we make an instance of this, if you take in the shape, which is an integer, we should take in the number of hidden units, and we should take in the output shape. Okay. With this, we make a sequential model where the first is to flatten it up. Okay. Because we want to fill it connected layer. And then we pass it through two linear models. So this is the first matrix, this is stoichiometry. Okay, so this is the setup. And then for the forward pass, we just call the self.layer. What is this layer? Layer is exactly this thing there, which composes of all this function composition. Okay. All right, so that's okay. We can now maybe make an instance of the model. Let's call it model 0. Okay. Send it to CPU. All right. So we want 10 hidden units in that model. So if you go back, this means that I'm going to have for the first layer, I'm going to have 10 by the input shape, it will be 784. The second layer is going to be 10, which is the output shape, by by 10. Okay, so that's that. So that gives me this model. Okay, so this is it here, 10 by 74 and 10 by 10. Okay, so I've set up the model. The next thing is to set up the loss. Okay, which basically says how well are we doing in model training. Okay, so for that, okay, I import some, some helper function from this same repository. Okay, where this note was taken. We will need them um, to display to use on my screen. Okay, so from the helper function, we import accuracy. By the way, you can also define this yourself. It's straightforward. There's no big deal. And then this is what we care about. We want the loss. Okay, because well, we know that we want probabilities at the end, so we use the quotient probabilities. Okay, all right. This tells us how well we're doing, and the optimizer essentially uses standard gradient-based learning algorithm like gradient descent, okay, or stochastic gradient descent in this case, with a learning rate of 0.1. So that's that. We've set up our loss and set up our optimizer, and we can just train it. Okay. So just for illustrative purpose, we set up a train time, which basically prints how long it would take for our model to train for completeness. So in this case, we just pass in the rise and then pass the total time, which is the end of when it trained and minus when it started. Okay. So at the end, this next start is just to set up the training loop. Okay. We use this TQDM to track our progress. And then we start the train time. Okay. And then we run the training. In this case, we're doing it for 3 weeks. Okay. Still the standard procedure. All right. So how do we do it? We set up a number of epochs as a loop. Okay. Within each epoch, we do the training. Okay. Because an epoch is a full round of training. The model has seen every data set once. That's one epoch. For 3 epoch, it means the model will see every data set 3 times. Okay. So this is where we now look at a particular data, the complete data sets. You can see that we are iterating through the training DataLoader. Okay, we'll set the model to training mode, and for each data we get, which is X and Y, we make a prediction, we calculate the loss, okay, and we can keep track of it so that we can print it eventually. So once we do that, we start the optimization process, which means for this very new loss, we want to set the previous gradient to 0. So 0 is that. Okay. And this we call back propagation. Okay. Which will recalculate these gradients. And once we are done, we can call the step method, which will change the weights based on the calculator gradients. So we do that till we are done with this batch and we're done with the involvement. Okay. Now this is a linear model. There's nothing to it. Okay. So this is epoch 1. It has looked at 0. It has looked at 5. And the end, it looked at 6,000 and it's training loss. So there's a 2%. This is the next epoch. So like I said, if you have any question, just put it up on the live chats. I'll do my best to answer. So we're on the third epoch now. Okay. Already we are getting an accuracy of 83%. It means it's getting the right answer is 3% of the time. With a loss of 0.1, okay. That's the test loss and training loss of 0.47, training loss of 0.47 as well. Okay. It took for this my computer, it took about 55 seconds for training in this video. So that's that. It doesn't look nice. I mean, 83%, not a bad one. Okay. So let's get more statistics from this model. So we evaluate the model. Okay. All right. So if you look at the output here, you'll see that for this very model version 0, we had trained a loss of 0.476. And we have an accuracy of 3%. Okay. This was trained on the CPU. We can set up this code so that it becomes agnostic to the device on the CPU. And what does that mean? It means that if I take this code and I run it on the CPU or on a computer with a GPU, it will automatically pick the available GPU. And it's a very simple line of code to do. So what do you do? This is what you do. Okay? So first you import touch, and then you ask if it has an available GPU. If there's CUDA is available, then you should set the device to be straight CUDA. Otherwise, you should set the device to CPU. So since I have this now as a variable, okay, I can now use it to hook up every model, every tensor, to move them either to CPU or GPU. But like I said, in this case, I don't have a GPU in this computer. So what you see is the CPU. If you run this same code on Google Colab, you will see the GPU, especially if you enable it, you will see the GPU, which means that this training will be a lot faster. Okay, so now let's go back to the model and try to see if we can make it better. Remember in the previous slide, okay, it will be forwarded to you by the guys from the admin. You're asking about the video. Okay, so let's see if we can make this better. By the way, like I said, what we set up here is a simple linear model. Okay, whenever you hear the word linear, just think of straight lines. Okay, so essentially what I'm saying is we are using straight line to be able to divide up the space for the data into different classes. Okay, now this very data set is very nice. Okay, it is somewhat linearly separable, so it's okay. But there are cases where the data is not linearly separable. So in which case we need to use some non-linearity. Okay. So let's look like how let's see how it will work. It's the same setup, but now I am adding a ReLU. Okay. So after I flatten it out, I add ReLU and pass it to a linear transformation. I squash out the negative numbers. Okay, this is what this does, ReLU. And I take it to 0, that's what it means. And I pass it to another linear layer, and I also process the next figure. So this is a version 2. Okay. All right, so we just make the instance of the model. Now, because we have set this to be device agnostic, I can make an instance of the model and send it to a particular device. But in this case, my device is CPU, so it doesn't change anything. But if you run this data set, it will now see the GPU instead. Okay, so my device is still CPU, so I can change this. I set up the loss like before. My loss function is called input loss with an optimizer the same unit. Okay. All right. Now I can, do the training. Okay, like I did before. All right, and see what happens. Okay. All right, so let's train for 3 epochs as well. So this will take a lot longer because now I have ReLU involved. Okay. So the training time is going to be slightly longer. There's more work doing this back propagation. Okay. And if you have a GPU, obviously this will take much faster than what it is. So this is very important. Okay, so it took about training time on the CPU was 56. Our previous training time was this is 55. So it's slightly slower than the first case. So this model is a lot more complex than the previous one. Okay, because of the management. So this took 56 seconds. Okay, but we didn't even do better. In fact, we performed worse. Okay, and maybe you can think about, ask yourself, why is this possible? One way to look at this problem is maybe we are overfitting more. Okay, what does overfitting means? It means that we are memorizing the training data, and by memorizing the training data, we are not generalizing well. So that is possibly one of the reasons why we have balance. Okay, so let's evaluate the model. Okay, so you even have the higher loss, S loss of 0.68 and an accuracy of 75%, which is less than what we saw. So for the two, so this is our new model, okay, and this is our old model. All right, you can see the first one does better, okay. The model is not so complex. We're just using the simple line to do the classification. Here, we're using curvy lines. So it could be that we are just learning every random noise in the data. And that eventually means that we are not going to generalize well. Okay. So now let's bring in the convolutional neural network. Okay. So for this, I have posted a few links just to give you an idea of what it does. So the convolutional neural network, okay, they are known for their capabilities to find visual patterns. What do they really mean? So how are they different from these, standard linear transformations that we saw? Okay. So with the convolutional neural network, we use something called a kernel. Okay. So you place a kernel on a particular region within the image, and you do a dot product between that kernel and that region. Okay. So if you slide it across, all right, you involve the image. Okay. So if you can still see my screen, I think I have a few animations. I don't think I posted it, but I'll post a link. So this is what we mean. This is a typical compilation. So what you have at the bottom here is the image. Okay. What you have on top here is a kernel. Okay. So in this case, this kernel is a 2x2 kernel on a 4x4 image. Okay. So if you see how the projection goes, so you take the 2x2 and put it on the region, Sorry, this is a 3x3 kernel on a 4x4 image. Okay. So if you superimpose it on the image and you do a dot product between that kernel and the image, you get a single value. So in this case, and you slide. So in this case, there is no padding. Okay. You have one slide, it means we move the kernel across one pixel. Okay. This is the situation where there is a padding. So the original image is still there, but we now padded it with extra pixel to make it larger. Okay. And the effect of this is that the output space, this output image, becomes larger. In this case, the output image is a 2x2. Now, because of the introduction of this one padding, the output image now becomes the same thing as the input image. Okay, in terms of dimension. All right. And this is still one stride. Okay. In the case of two strides, we move 2 pixels away. The same thing, this is 0 padding, 2 pixels away. Okay. All right. Now this is 1 padding, is still 2 pixels away. Okay. As you can see, because we are doing stride 2, the output dimension of the transformed image is much less than when we are doing strike one with one pattern. So this is how it works. So in a typical in a typical convolutional neural network, you're going to have several of these kernels, okay, initialized. And this is an example of what it looks like. So this is an area view of some I don't know what to call it, some medical scan. I think this is the chest or so. Okay, so this thing you see in red is a filter or a kernel. Okay, in this case, this is a 1 by 2 by 2 kernel, which corresponds, and if you convolve this on this image, okay, you are going to get one mark. So if you have 8 kernel, like in this case now, okay, it means each kernel, each filter will be one output. So the end, you're going to have a stack of 8 mark, okay, where each mark corresponds to a particular kernel. I don't know if that makes sense. Okay, and how exactly does it work? So this is an image. The thing you see in yellow, okay, indicates a kernel or a filter. So you can see that it is actually the dot product of that filter and that spatial location. Okay. So if you pause this animation for a while, you'll see that if you do the dot product, you get one output, and you slide that across to get the convolved feature. Okay. So that's about the convolution. Now, why is this special? It is because these convolutions can help us extract really nice features. Okay. And this is where the tiny ML visualizer comes in, this guy here. So let's look at it. Okay. All right. So this is a VGG network, a tiny VGG network. Okay. So you have one convolution here. You have a value. You have another convolution, a value, and a max pool, which is called the downsampling layer. And you stack this up, and you pass at the end, you have a frequency value. Okay. So if you pass an input, in this case, let's pass this input of a box. Okay. How does the feature input and output work? How the one model that? So that I'm just reading out a question from one of you. How the one model that if it were to be video? Okay, classification model. Also, why is the output feature one in the example you use? Okay, so like I said, okay, so let's look at this. You have one output feature for each filter. Okay, so in general, if you have 10 filters, you're going to get 10 output features. Okay, so an output feature corresponds to the filter which was used to convert. For the questions about video classification, a video is a sequence of images. Okay, so if you think of video classification as sequence of images, you can just use simple classification in simple image. Okay, and then you can run that through your simple object detection or whatever it is. Okay, with and like I said, videos are snapshots of images, so it should work and fire them. Except you want to do other fancier things, which I don't want to mention here. Okay. All right, so that's that. So what you see here is just to visualize. Okay, so I passed an input of a bus, okay, and these are the features that have been learned so far. Okay. Remember, I told you that higher values will indicate more activations learned for that very input. So it means that this layer here is where it learns a lot more about the bus here to this. Okay, and the bar under here indicates the class that input indicates. So in this case, this is a school bus. And yes, that's true because the input class is a school bus. You can always enter your own control your own image from your personal computer. Look at how those switches are, those activations are. Okay, so that's that. So with that said, we can incorporate our convolutional layer. We just put it before the fully connected layer. So what does that mean? We just use the 2D neural network. Now we specify one stride and one padding. So which means that we want the input feature dimension to be the same thing as the output feature dimension. We use the filter size of the kernel size of 3, okay? And then we specify the number of output channel, which corresponds to the number of filters or number of panels that we want to use for this combination. So we do that twice, the first one and the second one, okay? And then we done sample, okay? What this means is that given a particular kernel size, you just take the maximum within that way, okay? So this is not a learnable feature here. It's not a learnable layer because there's no weight to train. And the rest you can stack up as block 2, which is the convolutional block, okay? And then we can call the classifier as your fully connected loop, okay? So whenever an input comes in X, which is the tensor, we pass it to block 1. And what is block 1? Block 1 is this guy here, okay? And the result of that will pass also to block 2. What's block 2? Block 2 is this guy, which is extension. Okay? And lastly, we flatten it up, okay? All right? And pass it to our fully connected layer, which we call that. So this is this. Okay, and then we find that. So that is that for our model. Okay? So let's look at and this model is not trained by the way. Okay, it's not trained yet. Okay, so let's look at what happens. So let's say, for example, we just do a random image with backside 32, and it's a picture. So in this case, it's 3 by 64 by 64. Okay, right. So this becomes our test image. Okay, and we pick the first sample there. We take the shape. And we just basically look at what we have there. So in this case, of course, it's an image, so it's just zeros. I think I've explained what convolutions are and how to work about that. So for this test image, let's now see what our convolution does that is not training. So we make a simple 2D convolution with 1 stride and 0 padding. Okay. All right. So if you convolve that image using this convolutional layer, this is what you get eventually. Okay. Still a bunch of zeros on one. Okay. So if you look closely, you see that there are still some negative values. And if you pass that result to a array, you get rid of the negative values. So our test image originally is 1 by 3 by 64 by 64. Okay, but after convolution, you can see that the image resolution increases. Okay, because for this very convolution, we're using 0 padding. Okay, so that is what you see here. Okay. So this is before convolution, 1 by 3 by 64. After convolution, we now have 10. And why do we have 10? Because we specify that for this very convolution, you need 10 output channels. Okay? It means 10 random filters. Okay? So that's that. All right? Okay. Now, let's now try for a different stride. So the first one we did was stride 1. Let's look at stride 2 with 0 padding. Okay. So with more stride, you can see that the spatial resolution has decreased. It's now 30 by 30. Okay. All right, so we can also visualize these weights. Okay, all right. So the weights are okay. We have 10 of these filters. Each of them is 3 by 3. Okay, so we can have a look by calling probably a 2 partition. Okay, so there are 10 of these. Okay, each is 3 by 3, and of course their respective biases. Okay, because since they are 10, their biases will also be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's that. Okay, all right. So curve layer 2, the weights that the 10. Okay. We put channel that this is 5 by 5. So I think the last one is 5 by 5. Okay. Yeah, 5 by 5. Okay. All right. And the bias also depends. In this case, there are 10 bias. All right. So that's that. Okay. What about the max pool? Like I said, the max pool essentially just takes the maximum within a spatial location defined by the time. And it's not a trainable parameter, it's not a trainable layer. Okay, you're just taking the maximum within the particular. Okay, so with the kernel size of 2, here we need a max pool layer connection 2. We pass it through our convolution, and then we pass it through. Okay. All right, so the original image is 3 by 3. The image without the unsqueezed dimensions 1 by 3 by 4 by 64. After going to the convolutional layer, this decreases the resolution to 62 by 62. And then after going to the max pool layer, of course, we are squashing the spatial location also. We now get 1 by 10 by 32 by 50. Okay. So this is still us playing around. So make another random size. This is now a 2 by 2 image. One bad size is a black and white image. Okay, I'll pass it through. I'll pass it through the mask pool layer. Okay, because it's a 2 by 2 image, the output you get is just one number, which is this. All right. So that's that. Okay. So we can, I think at this point we are ready to, yeah, you can look at the CNN Explorer to get a better view. Okay, because that uses a pre-trained model called tiny BGD. So for this new model, we can set up the loss just like we did before. Okay. That's that. And then we train. This time we also train for 3D box. Okay. Let's now see how our new addition, what our new addition does to the model. It will take slightly longer because this is now a much more complex model. Okay. But hopefully we should get a better result. Okay. Thank you, Abraham. Thanks for the kind words. All right. So, like I said, it's going to take slightly longer. Okay. But while that is going on, we can still look at what should I? Yeah. So let me. This is part of what I posted in the Telegram. You can follow this link. This is just to give you an intuition. It's kind of an interactive environment. So this also is a model that is trained to identify digits. Okay, these digits are 0, 1 up to 9. Okay. So I have this window here to just play around. Let's say I type the word 4. Okay. All right. So this becomes my inputs, pixelated. Okay. These are the 0 values. Okay. These are the places where I have 1. Okay. Now for these very inputs, you can guess how many channels do I have? Okay. I have 1, 2, 3, 4, 5, 6 channels. Each of these channels randomly initialized and with different values. And upon trained, these channels will learn different features. Okay. Now, this output, let's just focus on this region. Okay. This is the input image, and this is the filter. We are using, in this case, I have 1, 2, 3, 4, 5 by 5 filter. Okay. You can see it points, you follow the projection on where the input image is. That's where the kernel is placed on, and that's where the dot product happens. Okay. And that gives me whatever I have in this value. So if I slide through, you see, then you can see how we're doing the strides, and the convolution. So this gives me one output feature. This also gives me another output feature for another random filter, and so on. So we have 6 here. Okay, this is the first layer. All right. Okay. The next thing is downsampling, which is max speed. Okay. So if I click here, so here I am downsampling by 2 by 2. Okay. So it means I'm taking a maximum within that region. If you slide also, you see how it does downsampling. If you look closely, you see that this is a much larger resolution, but after downsampling, you have a smaller resolution. So this is the max speed. Okay. So you must pull on each of these output features. So there are 6 of them. So you have 6 output features. The max pulling layer is not significant. Okay. And then we follow it up again with another convolutional layer. In this case, you can guess how many number of filters we have here. We have, from the output features, you can tell the number of filters we use. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 output filters. Okay. All right. And what is the input shape of those output of those image? The input shape now is 1, 2, 3, 4, 5, 6. So we have the batch size by 6 by the size of it. Okay. And then we are now convolving with 16. So it means we have 16 output features. Okay. We downsample that again, and then we stretch everything here into one large vector. Okay. We even, I think, okay, so we downsample. Oh, this is the fully connected layer. All right. And then with the same thing again, we reduce the resolution, and then I have a fully connected layer. Okay. So this is now our output prediction. The point where we have the lighter color indicate tells us the most probable classification for this my input. So here it is telling me that this is it's closely, its first prediction is 8. The most probable one is 8, and the second guess is 9. As you can see, because this is highlighted now. Okay, which is terrible. Maybe it's thinking that this, I don't know how we should pour this and so let me clear this. Let's put a 0 here. See, all right. Okay. So these are my inputs. All right. Passing through these, convolutions and downsampling. And it is telling me that it is most probably a 0 or a 3. Okay. A 0 or a 3. So this is what I posted in the Telegram group, just for you to have this visualization and get a better understanding. If you like, you can hide, all right. So this tells you that this is my first convolutional layer. I just hit okay. If I show this one, this is my downsampling. Okay. Show the next one. This is my second convolutional layer. Okay. Followed by a downsampling. Okay. And this is my first fully connected layer. All right. And this is my second fully connected layer. And this is out. Okay. So that's this visualization to give you a better understanding of of how this thing works. So let's go back to our notes, and we're done. Okay. It took us a lot longer. It took us 313 seconds, but now we are getting a better training accuracy and a better test accuracy. Okay. And let's look at it. So we had a much better loss, all right, with a better training accuracy, with a better test accuracy. Okay. So we can compare these three models in terms of the training time. Okay. This one was faster. This one is slightly slower, but the accuracy is less. This is a model 3 with the convolutional array. So these are the results. Version 1 with this low, version 2 with the higher loss, less accuracy. Version 3 with the lower loss and better accuracy. Yeah. Let's look at the training time also. Okay. It took a lot longer for the one with the convolutional neural network. So the more complex the model, the giveaway here, the more complex the model, the more time it takes to train. For those of you who are much more advanced, if you've ever trained the transformer model, the model used for ChatGPT, it takes months to train. So that tells you, that gives you an idea of how complex these things can be. All right. So we can look at a plot of these results, okay, in terms of the accuracy. So for the first model, version 0, we have 93, as I said. Second model has less accuracy, but the third model has more accuracy, but the trade-off that it takes a longer time to train. Okay. All right, so we can actually evaluate. So these are third model. We can actually see how well it does. Just visually see the data, see what they are doing. So this is what this one can make predictions. We take the model, take the data, which is the list, and then the device where we want to run it. Okay. So here from the test data set, you just take a few samples. Okay. All right, 9 precise. And then we append it here. Okay. So now we just take the shape and then the class name. Okay. So for this test image, all right, for the first test image, this is a today by 28, and it's actually a sample. But what does our model think about it? So let's see. So we get make prediction and pass our model version 2. Okay. And we pass this test sample that we just done. Okay. All right. So what do we have? So, all right. So the output here is 10 numbers. Okay. It doesn't really make any sense here because you need to pick the location with the maximum probability. All right. So here we just print out 2 or 3. Okay. To make better sense of this, we need to pick the arguments. All right. So that's the test one. So let's look at this also. Okay. So this is what I'm saying. For each of these outputs, we want to take the index with the maximum probability. All right. So remember, these are test samples. So to do that, we just get the predicted probability and take the argument with the maximum probability. Okay. All right. So as you can guess, the first sample, which was a sample, we are predicting that it's a 5 also. So this is true. Okay. And the same, and we also predict the label for the other way. So we can actually compare. So here we have the test label. So what we know, this is what we're actually predicting. Okay. All right, so we got the first one correctly. Okay, we got the second one correctly. We got the third one correctly. We got the fourth one, got the fifth one, sixth one, seventh. In fact, we actually got everything correct. Okay, so let's now visualize because they are the same. Let's now visualize what we are predicting and what we are true value. Okay, so this we predicted as standard, and the true value is also standard. This we are predicting as causal, and the true value is true also causal. Okay, this we are predicting as sneaker, true value is also sneaker. So we're actually getting everything correctly. Okay, so this okay, sneaker. I think we got everything correctly. Okay. Yeah, okay. All right. So you might want to see a complete statistics of prediction, and this is where something called the confusion matrix comes. Um, I, Sometimes I wonder what informed the decision for calling it a confusion matrix, but you can look it up, okay, and probably find out better why exactly called confusion matrix. Maybe it's a matrix that um, doesn't cause confusion, but sort of demystifies then the dynamics of the prediction. So the confusion matrix shows you where your classification model got confused, yeah, between the prediction and the true label. So to make a confusion matrix, we just go through 3 steps. We make predictions with our model. In this case, we're using version 2. And then we also make the confusion matrix using the library confusion matrix. And then we plot that matrix. Okay. So we can plot the confusion matrix using the plotting function. MLS extend plotting the plotting. All right, so that's what we're going to do. Okay. So in this case, we iterate through the first data loader. Okay. And then get the softmax. Okay. And then the arguments with the add max of each prediction, and then we store it as inputs. Okay. So we move everything to CP and append it to this list. Okay. Okay. All right. And then we can, oh, I'm not installed this module. So just give me a moment. Let me see how to do that before the time is over. So install watch. Just give me a few minutes while it installs this module. And hopefully when I run it again, it shouldn't have that. Okay, so that, let's see. Okay, I don't have MLS extend. So that also I install. Take a few minutes. Not sure. Come on. Okay. All right. So let's try it again. All right. So we're done. So we have all the packages imported and good to go. Okay. Now you can, show the confusion. So let's go it. All right. So this is our confusion matrix. Okay. Okay. All right. So obviously it's a matrix, okay, with all the categories. So on this axis, you have the predicted label, okay, On this axis, you have the true label. So on the main diagram and diagonal, it tells you all the labels that you predicted correctly. Okay. So it means for t-shirts, I'm predicting 884 correctly. For trousers, I'm predicting 964 correctly. For pullovers, I'm predicting 775 correctly. Okay. So what about these other columns? For t-shirts, for example, I predicted the t-shirt as trouser twice, 2. I predicted a t-shirt as pullover, 8 of them. I predicted 14 dresses as t-shirts. I did not predict any clothes. I got all the clothes correctly, all the sandals correctly. For shirts, I predicted 126. I did not predict any. I got all the sneakers correctly, and I predicted 2 bags as t-shirts. Okay. Similarly for trousers, all right. I predicted 3 dresses as trousers. I predicted 1 coat of the trouser. I predicted a bag in trouser, and I predicted a t-shirt on top of the trouser. So this gives you statistics of how well your model does together when compared to the actual data. So the last part of the program is, of the node is to save it. I mean, once you're done building a model and it's accurate, you might want to save it to a ghost, okay? So that you can reload it, maybe take that model and build a simple mobile app, okay? And then interface, and then use that model as a backend to that app, okay? To save a model in Python to start together, okay? Here, we specify the path, right? Okay. In this case, the path is model, so it means I'm going to make a directory, all right? And then I just give it a model name, all right? And then lastly, I'll save it, okay? Saving a model essentially just means you're saving all the trained weights eventually. So this is what this line does. When we are done, we've saved it to models, and this is the actual model. Okay? If you open up your code, this is the model I just saved. Okay? This one. 10 seconds. Okay. Now, if you save the model, you can also load it. To load it is super easy. Okay. So you get the architecture and then you just load it. Okay. So the architecture is this setup. Okay. Now we can just load the weight. Where are the weights from the save model path? And once I load it, then I can reuse it. Okay. This is the loaded model, and I'm using it to evaluate the training data set. And you can see the accuracy and the loss is the same. Okay. So if the model results are closed and the app is also closed, that's just closed. Okay. So that's that about deep learning optimization, optimizing deep learning. There are a few exercises here, okay, that I think will be helpful for those of you who are interested. And also, like I said at the beginning of this class, it will be best for you to, curate your own custom data. It's a lot more interesting if you go out in the field, or maybe you have a project that you care about. You go out, collect the data, and run these things that we just talked about. Then you will appreciate the beauty behind these concepts. So at this point, thank you all. I'll be setting up the the assessments very soon, okay, which will be online. So I advise that you start preparing for that assessment. If you have any questions, you can always, at the appropriate time, you can always send a message to the Telegram. I'll be more than happy to explain further. Thank you very much, and have a good day.